So for those of you who have not met him, I would like to introduce to Dr. Rafiqul Gani. At his request, he asked me not to introduce him and not write the short bio. So he retired from DTU in 2017, and as we know, he has been more active than ever in the academic area. So with that, we welcome Dr. Gani.
Okay, so thank you very much. For all those who are still here, thank you for staying on. And to the organizers, thank you for organizing this very good workshop. So I'm going to give a short perspectives in terms of what I would call the good, the not so good, and the very good. And I will also at the same time point out from the presentations that were given here, most of them I would say, or all of them are in the category of good and very good. Okay, so I say right at the beginning. So I will start with what we call a multi-layered view of process systems engineering. It's based on a view of chemical engineering. And to understand this, we can go from horizontally from left to right, meaning what is our core activity, what do we use as input, and what do we get as output of the core activity. And from vertically, from bottom to the top, what knowledge we need in order to perform this activity, and what is the result that we get from this knowledge so that we can perform those activities. So if you understand that from left to right and from bottom to top, we can see that our core activity is to convert resources that we have to useful products through a process. And in order to do that, we need knowledge, and knowledge in the form of modeling, knowledge in the form of methods for synthesis design, control, numerical methods, etc. And with this knowledge, we can model the process, we can design the process, we can operate the process, and so on. And then we can ask, is that enough? And I would say, no, that is not enough, because we are not saying what kind of resources, how much we have, what kind of product we want, is it the best product? So that is not enough. So this is the core, fundamental layer of our process systems engineering, but we need more. So we added a middle layer where we say, now we will augment our fundamental ideas with integration of engineering and science, AI, machine learning, MPC, PI, whatever abbreviations you can think of, you can put them there, but we augment our fundamental ideas. And through that, we can get sustainable process that we have already heard. And so a lot of the presentations, I would say, from the academia are in the middle layer and the outer layer, which you will see. I would say a lot of the presentations from the industry were in the fundamental layer. So now we have sufficient, sustainable, efficient, reliable technologies, and then we can ask, is that enough? And I would say, no, that is not enough, because we need to know about the location of the resources, the recovery of the resources. Is the product optimal? What kind of waste do we have? How do we recycle the waste? All these things also need to be. And a more fundamental question, how do we serve the society? So then we put, that was the core layer, then we put the middle layer, and now we add the outer layer, the outer unifying layer. And with that, we can say, we can take all kinds of questions related to the resources. We can answer all kinds of questions with respect to the products that we want. And finally, at the top we can see we serve the society by providing answers to circular economy, sustainable development, and so on. So now, with that as the background, I will try to touch on not all the topics, just some of the topics. And the first one, which is my favorite, modeling, model-based systems. I could talk a lot about this. So the way I look at it is, we have the system that you see on the top right corner, and we are trying to make a model which is below the darker green. And the question is, are we trying to model everything of the system or part of the system? That depends on what kind of problem we are solving and whether we have the right model or not. And once we have the model, and I would say modeling is the activity that develops and tests the model. So just having the model is not enough. Do we have a procedure to develop the model? And here probably we need to do more. Once somebody was presenting a model in a conference, and I asked, how long did it take you? He said 3 years, my PhD. So can we reduce it to 3 months or 3 days? It should be possible if we can look at all the modeling steps and where the computer can do things much faster than the human can do. But that doesn't mean I want to replace the human with the computer. So don't get the wrong idea there. And then if we have the model-based system, what kind of problems can we solve? And here I would also add, and this is a quote coming from a statistician. He's an expert, world expert statistician, who says all models are wrong, some are useful. And at the same time, I will put also from the Oxford Dictionary what is meant by surrogate. Surrogate is an approximation of the real system. So if I take these two combined together, does this mean that all surrogate, which is a representation of the real system, are wrong or approximate? And then when we write, or I've seen so many papers that I get for review, which says process optimization based on surrogate model. It immediately tells me, why is the author telling me that he has the wrong model? Can I trust these results? So I would like to raise this question, why do we have to write surrogate in our title of the papers? Because it's approximate. We are saying it is approximate or it could be wrong. And to me it gives the wrong impression. And now, based on this, let's take the system, because we are trying to solve problems of the system, whatever that system is. And we have all kinds of information coming into the system. And here I put not just data, we have material, energy, water, money, people, whatever you can think of. And based on all these things that are coming in, and we want to improve the system in different ways, we can get all kinds of output. And so we need to solve the problem of the system, and we get those output that we desire. And here we can say, we have to define which problem, that means which activity that I mentioned in the multiple layers, how to define this problem, and do we need a good understanding of the system and the problem. And I would say it is very important to have a good understanding of the system. And one thing I would point out here is that we are talking about processes, chemical, biochemical, food, pharmaceutical. All these processes need to satisfy some fundamental laws. And one of those principal fundamental laws is the conservation principle. We cannot, just having data, we cannot just ignore the conservation principle. And if we take the conservation principle, we will have waste. If we take whatever comes in, goes out, the difference is waste. And if we don't take that into account, we have a problem. And if we just use data, which is not satisfying the conservation principle, can we use those data? It's something to think of. So now I will try to give some overview of some problems. One is that whatever problems we are solving, we are making some decisions, and that decision requires management of enormous amounts of data, information, knowledge, so that we can solve the problem. And the first thing is, as we saw the system, where is the system boundary? Depending on the system boundary, we can solve the right problem or the wrong problem, or go to the wrong conclusions. We have a lot of data, and for me, it's not a question of whether we have enough data. What my question is, do we have the consistent data that I can use? So maybe we need a filtration of the data to solve the problems. And then comes the last one, the model. Of course, we do not have all the knowledge to make a model without any parameters. The only model there is the universal gas law, which applies only for the ideal system. Anything else, we need some parameter. But we can perform these miracles, and everybody is performing this miracle almost every day, because as soon as you have a parameter and you have data and you fill the parameter, so the one who made this cartoon probably did not know us. We do these miracles every day. So the question here is, are we able to, by solving the problems, influence the decision makers? Maybe we have a problem of defining the boundary, of using the wrong data, and maybe even the wrong model. So I come back to the system, and I will try to highlight some of the issues, not all the issues: the problem definition, the system boundary, decisions that we are going to make, verification. There could be many more, I'm just highlighting a few. And which problem to solve, how to define the problem. Do we need a very good understanding of the system? So in my view, and also when we want to solve the problem, any problem, we need to define some targets for improvement. And those targets need to be convincing arguments. And we should find, with very good convincing arguments, that this is the problem. And this is why we want to solve this. So what is a good development? I would say acceptable, defined problem. People can understand that. Some understanding of the system, not perfect, but some understanding of the system. Model-based design decisions, if the model is at least qualitatively correct. Does not have to be quantitatively correct, but at least qualitatively correct. I would call that these are acceptable, good developments. I would say not so good, unclear problem definition. We don't know which subsystem we are talking about. Unclear also system understanding. And I'm biased, but maybe in this I would say just based on data, we cannot make decisions. We need, at least in our case, processes that we are talking about, some fundamental principles need to be satisfied. So we cannot ignore that and just take the data and make decisions. So that for me would be not so good. And very good would be a clearly defined problem, very good understanding of the system, and not just data and not just model, but a combination of data and model, and that gives us the basis for decisions. So that those, and I would say presentations here were in the good category and in the very good category. There were no, I would call them, that were not so good. But a lot of papers I received are in the not so good category. And a very good problem definition and solution of the problem. I was for 10 days earlier this month in Argentina, and there they talked about, they have this lake which supplies the water, which has fish, which has birds and others, which has plants, and it has multi-purpose lake. They need to maintain the concentration of the organisms, microorganisms, all these things in the water. And the water should not vaporize out. There are so many other problems. They try to understand the system, develop the model from first principles. Of course, there were many things they did not know. They put the parameters, they collected the data, fitted the parameters, and actually improved the condition of the lake. Sorry. Oops. I'm going in the wrong direction. Okay. They improved the condition of the lake, and they could provide, taking past data, point out in the immediate time how the concentration of the water changed, the fish became more healthy, the plants became better, all of these things they could predict. And they were able to convince the administrators of that province, and it was so convincing that another province now would like them to do the same modeling. So this is what I would call a very good development, and it's using process systems engineering things. As soon as we get the model, which is in this case differential algebraic equations with parameters, we can solve those. That's no problem. So now I will show another modeling aspect. We have data about chemicals. So all the two plots you see are data, pure compound data of chemicals, and we would like to predict the property of those chemicals. One way is represent the chemicals by some descriptor, and then use what I would call the concept of additivity. If we can put different summation terms are contribution, additive contributions of different classes of descriptor. So here there are 3 classes of descriptor, and we can predict the property. So this concept is also, you can think of that if we have infinite number of classes of the summation terms, we have the perfect model. But we are not going to have infinite terms. What is a finite term? And here is 3. Can we have more? So that is, I would call, simple, qualitatively correct, group contribution based. And we can have 20, that is the hidden layer, number of hidden layers, based on machine learning. The difference is we have 10% approximate error, and they're 1% or less. So it's very accurate, but it's not surprising. We have 20 times more parameters, 20 times more information. And the model is black box, we do not know. This one we can calculate by hand. So here are some statistics in terms of storage and computing time. But now I want to show you something else. And we have the data on the left, and I talked about filtration of the data. On the right is the filtered data, and what you can see are different trends. So if I can find 20 trends like that and model each of them individually, I actually have the 20 hidden layer model. Now if I tell or write a paper saying I have 20 models, they will throw out the paper. But if I say I have 20 hidden layers, it's perfect. So is the ML telling us one way of cheating? Because this they will say, no, you're cheating. But if we do it hidden layer, it's not cheating. And the other thing I would say is that this filtration and then developing the model is human learning. It's not machine learning, it's human learning. I'm learning by trial and error, finding out the 20 trends, and then I'm making the model. So why do we spend so much time teaching the machine and not us? We could teach ourselves and do that. Then so I go from modeling now to the synthesis, design, analysis, and again I will show you some what I said in here, not so good, not an issue, and does not make sense. So the first one is not so good. I see a lot of papers, almost one every week, that says we have done the optimal product design based on one property. And so if you look at those circles, red would be the solution of based on one property, and the blue and the other one are based on. So if we just take one property, how does it become optimal? As soon as we put another property, it can go out of the feasible range. So we need to define the problem correctly and consistently so that we can say optimal. And optimal until we have even identified the molecule, until we have applied it, until we have made the process, saying it is optimal makes no sense. Then there is a lot of work these days. People are claiming they use generative AI or graph neural network or GCM or other things. They can generate all molecular structures. And I would say that is not an issue. There are databases now with 12 million chemicals already. People have found it, and you can find it in PubChem. So what is this big issue of generating all these chemicals? It's already there. And I found out, I created this table more than 20 years ago. And all I did was write a program with 4 do loops. It's about atoms and bonds. And if you fill up atoms and bonds, you can generate all these structures. Our IT system at DTU were making some issues with me about the server. I put this on the server and got the server to crash. So it's not an issue at all. People should look at the chemistry books. It's fundamental, basic, atoms and bonds and nothing else. So it's not a big issue. Then does not make sense. This is now, it looks like a very hot topic, that you see this molecule here. In pharma they say that this is called a benzene dog. It looks like a head with a body, and a lot of the drug molecules have this as part of the structure. So we can take this structure and we can add other atoms and try to see if we can get a molecule, a drug molecule. So some people are claiming that they can generate these molecules and find a good candidate for a drug. Well, first of all, to generate all chemicals that have a benzene ring in the database are already there. And then without screening, it does not mean anything. So if we then say, well, for cancer we need this property, then we can find out of those millions which ones. So being able to find that and claim that they found some good candidate is just misrepresentation of the information. So, and what I will point out here is the important thing is the context. Without the context, generating the information is already there and it serves no purpose. And the same thing I will say about the process. So here is a part of a process. People have done generative AI and said they can complete the process, auto-completion. So what I will say here, and these are 3 candidates that they have published. And everybody is thinking, oh, this is so great. But I think you should ask the question first. Out of those 3 flow sheets that you see, which one is correct? And I would say it could be that all are wrong, or maybe one is correct. Because if I look at the possible reactions that could take place in the reactor, there will be different kinds of reaction, different kinds of chemicals, different number of chemicals. And without taking those information, all those flow sheets cannot be generated, or they are not feasible. So what is important here to note is that flow sheet representation is not just a drawing, and this is the mistake that these people are making. It's not a drawing. There are chemicals involved, there are operations involved, and without knowing those, just making the drawing serves no purpose. And if you want to know more about this, so this is an advertisement. On the 29th of May, we are going to have a webinar where we will discuss these and other issues. So there, it is generative AI with context, with modeling. Now I go to the next step, that we have talked about all these complex problems that we want to solve. And we have the process simulator, which I would say is a good development, but there are problems that we cannot solve. But at any time, somebody somewhere is using a simulator. So that's a very good development coming from process systems engineering. But it cannot solve the problems if it does not have a flow sheet, if it does not know the catalyst, if it does not have the unit operation or model. So how do we take these into account? So if we think that just because process simulator, I'm also taking into account all the summary, so I should get 2 minutes extra.
I'm not going to argue.
I will finish within 5 minutes. So we need, just the process simulator is not enough, we need additional tools. And this is where I think we need to develop those additional tools so we can go beyond. Process simulator will only verify our decisions, but it will not make our decisions. So we need to understand that. And so the kind of problems we would like to solve, and I think in the presentations, many of the speakers also talked about integrated approach. You see in the big superstructure, we cannot get away from the superstructure. That is the process, but we also have how we generate the power. So that's another superstructure. Water, another superstructure. Can we combine all of these to find a net zero, net negative problem formulation and solution? So something like that would be a very good development as far as I'm concerned. So now I will finish with 3 perspectives, so finish on time. And these are, I will agree, these are biased opinion, my own personal interest. So some examples of very good development, organic synthesis, I think is very important, because even if we want to do biorefineries, biochemical, bioconversions, CO2 utilization, we need to generate new reactions. So organic synthesis is very, very important. Chemical substitution, it was also mentioned before, is very important. Process intensification, better healthcare management, safety management. I forgot to include something here. Are materials. Materials is very, very important. Examples of development not so good. These are based on papers I reviewed, and these papers, despite my objections, were published. One was smart optimization, very good maths. The only thing was that the application was for a separation with one solute and one solvent. For that problem, I could write the equation by hand and solve it by hand. I don't understand how that got accepted by the reviewers, other reviewers, and the journal. Another one was need for surrogate. They said very good need, high pressure, temperature, all kinds of things. They developed the model, but the case study was at 1 atmosphere, limited temperature difference, almost ideal conditions. I didn't need the surrogate for that. I didn't need, the original model did not have to be PSE SAFT and things like that. The last one was high throughput screening, machine learning, all these things, all involved in one paper. In the end, it was 5 solvents that you can find in the database. And 3 of them are in the banned list. So, things like that get published, we have to be careful of it. And then, whatever developments we make, very good developments, very good advances, but we depend on other people to make the decision on whether to take those or not. So, you give us a problem, we can find the technical solution, but other people are trying to make the decision whether that technical solution would be applied or not. So, I think we need to take care of, we should make the decisions and we should be able to influence the decision makers better. So selection of problems that we need to solve, we need to revisit that. Correct, convincing arguments need to be provided. False promises should not be made. Generative AI without context is a false promise. Finally, method for systematic solution of problems by efficient management of complexity. That is what we should be doing. What are the issues? I've just listed them, including ChatGPT, generative AI, machine learning, and so on. And what I would suggest is consider domain knowledge to define the problem. We should not forget the fundamental principles. Use appropriate computers for speed up. We cannot solve hundreds of equations by hand. We should use the computer that can do it for us. Apply AI, and here I would put also human intelligence to reduce the complexity. And we should be able to do that. Use appropriate numerical methods plus machine learning plus human learning to efficiently and reliably solve the problems. With that, I finish. Thank you.